Hi everyone, welcome to another season of the video series to learn about cutting-edge technologies for your data center. In the last series, almost 2 years ago, we discussed BGP unnumbered, RDMA over Converged Ethernet version 2, otherwise known as ROCE V2, and IP fabrics from modern data centers. Well, as you know, recent advances in generative AI have captured the imagination of hundreds of millions of people around the world. Data centers are the engines behind AI, and data center networks play a critical role in interconnecting and maximizing the utilization of costly GPU servers that perform the compute-intensive processing in an AI training data center. Today, I'm joined by my special guest and a good friend, Michal Styszynski. Michal, always a pleasure to sit down with you and discuss cutting-edge technological advances in the data center space.
Hey, Arun. Hi, everyone. Thanks for having me, Arun, today. You are absolutely to the point, Arun. As a matter of fact, after 2 years, we see that the technologies we discussed just after the COVID era was ending, we realized that in the last 2 years, the technology of RDMA over Converged Ethernet just exploded in terms of popularity. While we can say that the baseline of the technology stays the same, actually the way we use it changed a little bit. And that's, of course, in the context of the explosion of the popularity of the ChatGPT, large language models, artificial intelligence, and machine learning. So when building these infrastructures, we need a lot of parallel processing capacity at scale. So it means we are using additional components inside the server, such as the GPUs, which are accelerating the way we can treat the data at the same time in parallel, right? So instead of using the CPU approach, which is a serialized approach of processing data, using the GPUs, which are in the same server, we can actually process the data in parallel at the same time and deliver the outcomes to the user quickly on time, right? So in order to exchange the data and have the cycles of the data processing to occur on different servers, we need a technology to actually synchronize the data between the servers. And one of these technology is, in fact, the ROCE V2 we discussed over 2 years ago now. Did anything change, right? You wanted to make sure that we are actually up to date about this technology. So there are some components that changed. Popularity of the technology increased, but there is a reason for that also. Is because simply the technology is offering much more better resiliency comparing to, for example, a centralized model of InfiniBand, where there is also a controller which actually, gives the access to the resources of the fabric. In case of Ethernet IP fabrics, where we transport the InfiniBand across the fabric, we have a fully distributed architectural model. So that's one of the advantage. So what's changed comparing to what used to be is, for example, the scale actually requirements are much bigger now, right? So we have, for example, the concepts of running dedicated ROCE V2 networks in the backend of the AI/ML clusters, and that's where also the technology is used in the leaf spine, super spine type of deployment. But the oversubscription ratio, for example, is 1-to-1, comparing to what it used to be traditionally in the data center deployments, where we had like 1-to-3, 1-to-2, sometimes even 1-to-6. So in this case, even if the oversubscription ratios from leaf to spine goes to 1-to-1, in some situations, still ROCE V2 will play a significant role. It's also the case whenever we have a rail optimized deployment where actually we connect the GPUs on the same switch, but then we have interconnectivity between different stripes of the leaf devices to go through the spines. That's where also the stripe-to-stripe connectivity may require the ROCE V2, which is available in the industry for quite some time now. So that's what's changed, right? Some architectural aspects, some additional things that we'll be discussing later on probably, but we definitely see that there are advances which actually confirms that whoever started to work on this technology some time ago did the right choice in terms of decision-making process.
Fantastic.
Yeah.
I'm glad now that we understand the value of the technology has increased over time, especially
True. Yeah.
nowadays when we are hearing more about Rocky V2. Uh, that brings to my next question. How are the Rocky V2 components coordinating inside the DC fabric? I recall the two components, particularly the PFC and the ECN inside the IP class fabric.
No, it's a good point, Arun. So, in fact, you cited the two big components. So, I mentioned in the first part of our discussion that we want to transport the payloads of the InfiniBand using the UDP encapsulation across the fabric. So, between the leaf devices from one GPU to another GPU, we are just syncing these chunks of data using the transport over Ethernet IP UDP. But the two aspects that are important here is to make sure that whenever there is a congestion that occurs on the network, that we actually handle this congestion in the right way. So you have these two mechanisms: priority flow control using the DSCP markings and also the ECN, right? So now the question is, once you get into the situation with the congestion, which one will kick in first, right? So quite often it depends on the implementation. In case of most of the implementations, we have the ECN, which will kick in first, and will actually send on the data plane packets markings of the one-to-one into the destination GPU. And so the destination GPU will realize, okay, there is an information that I have some congestion, so I need to react to it, and it's going to send the information to the originator of the flow, right, to slow down a little bit. And then if after some time there are still congestions occurring, only then the PFC will kick in on the back end and then will inform one by one, hop by hop on the point-to-point level that there are switches down the road to slow down the speed at which the data is being sent, right? So there is that level of coordination at the per node level for these two mechanisms that you mentioned.
It's good to know that the components of Rocky V2 are really well coordinated inside the fabric. But how can an operator be sure that they're really working?
Oh, that's a challenging actually question, because as a matter of fact, let's be precise. So the mechanisms that we discussed, the ECN and PFC, they are acting actually at the sub-second level, right? So we talk about the microsecond accuracy here. So it's fundamental to make sure that actually at the switch level and the actually lower level of the ASIC, we have also the components which are capable of tracking the occurrence of the congestions. So let's take a simple example. So as an operator, I want to make sure that my GPU fabric, my AI/ML cluster fabric, is actually in the steady state. So I'm checking on my monitoring stations that actually the occurrence of these congestions is pretty low, right? In case I see them on and on being triggered, it means that something is wrong in my design, or my settings of my fabrics are not good, right? Or maybe I oversubscribe my infrastructure. So it's important to make sure that we have this ECN and PFC telemetry information streamed at the per queue level to the station, such as, for example, the abstract fabric manager, where we can visualize, okay, for this component on this component of the fabric, I do have some situations which I need to fine tune, right? So that's the example. And so we can see on the slide, we have this capability of visualizing also the buffering utilization, right? So that aspect of buffer is key, because it means that as long as I'm utilizing intelligently my buffering at the egress ports in my fabric, then in theory, I should not trigger any of these PFC or ECN mechanisms, right, to control the congestions, right? So monitoring, having the telemetry for Rocky V2 per queue is instrumental, right, to make sure that we have a full understanding of the performances of the fabric.
So besides the ECN and PFC monitoring, are there any more advanced Rocky V2 capabilities?
Well, yes, we have situations where actually we can mitigate some of the situations where, well, the fabric may be a little bit in a wrong situation where the congestions are occurring. And so we want to make sure that the occurrence of the congestions inside the fabric are not actually having repercussions on the rest of the GPU workload exchanges, right? So there is, for example, a functionality called PFC Watchdog, pretty popular in the industry, where we actually want to go through this situation where if there is an avalanche of PFCs which are received on the ingress port, that if we consider that this avalanche is a continuous rate of the PFCs, so the pushbacks are received on and on from a specific upstream switch, then we can consider, okay, this is not a normal situation, and we can simply ignore these packets, right? Ignore these packets instead of pushing them down to the downstream switches. We will simply say, okay, I ignore these packets, or eventually, as an option, I can say, okay, in order to mitigate that situation of the congestion on that specific queue, I will decide to actually drop the packets in order to stop the congestion on a specific segment of the fabric, right? So it goes through the distinct three states, this PFC Watchdog implementation used on a specific node. We have this on the diagram where the spine 1 was enabled with the PFC Watchdog, which is actually spine aggregating connectivities from different leaf devices on which the GPUs are connected. And so the detection timer will actually go through the cycle and check how much of these PFC messages were received. And so if it considers that in the window of time it received too much of this, it's going to just simply say, okay, probably it's not a normal situation, so I'm going to ignore them instead of penalizing all the rest of the fabric from the slowdown, right? So in order to conserve the good performances for all the rest of the GPUs, I will actually consider this as a function to control how actually the reach of the PFC is spread across the fabric. So pretty good function. Whenever we rely a lot on PFC, I think it's worth to consider that kind of mechanism. So that's one. And then there is another one which is trying to help actually optimize the way we use the PFC, the priority flow controls, is the PFC X on, X off. So whenever we discuss the Rocky V2 PFC priority flow control, we also need to think about how the buffering utilization happens. So if we have a topology, you can see on my left-hand side, so we have the leaf spine, the topology, where actually on the ET2 of the spine 1, there was a congestion that happened, right? So in this situation, well, we need to think about at which moment I should start generating my, for example, X off messages, which are the PFC control messages, which are saying to the downstream device, in this case, for example, the leaf 1, to actually slow down, keep in buffers a little bit the packets instead of continuously send them and then get the congestions on the ET2 of the spine 1. So as you can see, we have this opportunity here to actually control the shared buffer utilization at the per queue level by setting something that is called alpha values. So by setting different values for the alpha at the per queue level, we can actually control how often actually the X off messages will be sent, right? So if, for example, I set my X of alpha value messages to a higher value, then the chances of the occurrence of the PFC will actually go down, right? So if you see on the left-hand side, we have a typical buffer thresholds, and so the X off, X on, as well as the headroom, they are representing these three thresholds, and in function of the settings of the either alpha value or X on offset, we can control actually on how often the PFC messages are actually triggered, right? So in order to be actually a little bit more precise, it's always better to take an example of it. So I have an example of a simple topology. We have the two ports, ET0 and ET1, connected on the same switch, for example, a QFX 5230. And then we have an outgoing interface, ET20, right? So in this situation, we have on the same outgoing interface two queues, Q0 and Q3, and they are set with two different X of alpha values. So let's say we decide to set the alpha value of 9 for the Q0, and then the alpha value of 7 for the Q3. So you can see that depending on the values of these alphas, the outcome is that I'm going to get a different number of cells, different number of buffers for each of the Q. So I share also the formula on how we can actually calculate, fine-tune these buffers. And so in reality, where exactly we would consider such advanced, complicated calculations. Mm-hmm. So we may have situations where actually the specific large language models are more important in terms of data processing than the others, right? They need to get the data synced faster, right? So for these kind of large language models, we don't want to actually slow down the data exchanges, and so we would typically allocate higher alpha values, right? That's one of the examples. So we can see we have these two functionalities I explained. One is the PFC watchdog, the other one is the XOF alpha values, where actually the administrator of the fabric can fine-tune the fabric to make sure that if he gets the best of the bandwidth deployed in the fabric, so with the best of the bandwidth of 400 gig, 800 gig deployed in an AML cluster. So I think this is important, a little bit more advanced, but this is what actually the industry is proposing to make sure that actually these AML cluster deployments are really good in terms of performance and then can scale at a larger volume, right?
This is interesting. As these advanced options for Rocky V2 help to get the proper congestion control settings. But as the enterprises and the cloud providers are building the AI ML clusters, are there any other technologies that they must consider, Michael?
Good point. Actually, the aspect of innovation still is increasing, right? In the context of AI/ML clusters, there is even more innovations in terms of software, where instead of having traditional load balancing mechanisms, there are a lot of more efficiency which comes into play, especially when you consider the AI/ML workloads. The entropy of these workloads, so the variation in terms of characteristics of the flows are relatively low, right, comparing to traditional server type of communication. So in order to make sure that we still use the max of the capacity of our AI/ML cluster fabric, there are a lot of enhancements around the load balancing. Some of them are, for example, the dynamic load balancing, where the characteristics of the flow are not the only entry, but also the bandwidth, the real-time bandwidth utilization of the outgoing links on the IP-CMP groups are incorporated in the calculation of the hashing. That's one example. Another one is, for example, the GLB, the global load balancing, where actually we track also the situation on the next to next hop node in order to check what are the performances on the next hop nodes in order to consider the right path locally on the device. And then the last one is the traffic engineering inside the fabric, where as the administration task, we can decide, okay, that there are, for example, elephant flows and mice flows that they're going to always go on two diverse paths inside the fabric, and we'll have a control on which of the next hop they're going to use. So a lot of advancements, a lot of innovation around also load balancing, right, which is key inside the AI/ML cluster networking, Arun. Right.
Awesome. So once again, thank you, Michael, for just being patiently answering a lot of questions. And this is going to be great because I'm learning a lot of new things as well as we talk. And thank you to all the viewers. My suggestion is going to be stay tuned to learn more about the AI data center networks in our next set of videos. With that, have a wonderful rest of your day.
Thank you, Matt.